2 remaining talks today. So first, we have Joe telling us exciting math things.
Thanks. So this is going to be like maybe dessert for your lunch, hopefully. Just observation about symmetric states. So I guess so. In quantum information, if you have some fact that's a generalization from classical information theory, it's like often interesting to understand what's extra or special in the most quantum instantiation of this theorem. So is it just a raw extension of something about classical distributions, or do weird phenomena appear? And I want to explore an example of this in the setting of De Finetti theorems. So we can just recall the quantum De Finetti theorem. It's in the simplest instantiation. You have some rho, which is a density on n qubits. And we'll use rho sub m to denote the marginal on any of the m qubits. It's any of them because I forgot to mention, rho here is symmetric. So if you permute any of the n qubits, it stays rho. Rho is mixed, so this doesn't necessarily mean it's in the symmetric subspace, but it's still symmetric with respect to permuting qubits. And for classical distributions, and now also for quantum states, we have this lovely kind of structural fact, which says that small marginals of the state roughly look like a classical mixture of what you could call IID quantum states, 1-qubit states. So in particular, for all m in n, there is some measure mu on 1-qubit states such that this marginal, rho sub m, is well approximated by this mixture. So integral of sigma to the power m d mu of sigma. So this is just a 1-qubit state, maybe mixed. And this distance is trace distance. And the approximation improves as the marginal gets smaller. So it goes with the ratio here. So this is a classical fact in quantum information, and it's a direct generalization of the classical fact when the density is diagonal. Okay. So I think it's kind of interesting to think about what might be special about this setup when rho is like maximally quantum. And here, okay, maybe any suggestions from the audience of like what we should treat as maximally quantum in this setting? Just, okay, so one thing is it should be pure. That seems like maximally quantum. But what if it's a product state? What if it's pure and a product state? Then this still feels pretty classical, because up to a local change in basis, it's basically a point mass, right? It's still diagonalizable in some product basis. So we should think of, maximally quantum as pure and far from product. Okay, so with this in mind, I want to motivate this new observation with a question, which is, what does rho sub m remember about rho? So if rho is fully classical, basically the answer is nothing. So if rho is diagonal, let's say, it can be nothing. What do I mean by that? There are densities, classical densities, which are far, let's say, far from uniform, but as soon as you remove a single qubit, it becomes a uniform distribution. So if you only look at, a little piece, you can learn basically nothing about the global state. what we'll find is that actually in this kind of maximally quantum setting, rho sub m does remember something. So I don't totally know what's a good name for this, but we can call it rigidity for Definetti. And it's the following. So let psi be pure, symmetric. Then for all m in n, the distance of this marginal psi sub m, which could be mixed, from the set of product states. So product states could be mixed product states. I do not mean like separable. I mean really a tensor product of maybe mixed things is actually controlled by m over n times the distance of psi from product. Here. Yeah. Yeah. So, okay, if you want trace distance, you have to put a square here. This we can think of as the infidelity, is what this is literally for. Yeah, and so it's kind of funny to compare these things, because we do know that marginals are always separable in some sense. So what this is saying is that if psi is pure and far from product, then this marginal that Definetti's handing you, sorry, this decomposition that Definetti's handing you, the mu cannot be a point mass. It needs to be like truly non-trivial distribution. You can also kind of think about how psi sub m forgets as you increase m, or sorry, decrease m. So, okay, I'm drawing a picture that's directly interpreting what I wrote here. So m equals n over here, equals 1 here, n minus 1. And what this is saying for psi, let's say psi far from product, this is d psi sub m prod. What this is saying is that as you forget qubits, there's like a linear lower bound about how quickly you can approach. So the curves are different, of course, depending on whatever global state you're working with, but you can't become superproduct too quickly. Yeah, and then, so okay, this is, yeah, any questions about this phenomenon?
Just to be clear, it's product, not mixture over product.
Exactly right, literally product. Yeah.
Because I guess like if your state is just like a cat state,
Yeah.
then you'll always be a mixture over two.
Yeah, exactly right. Yeah, and but it's like solidly two, like significant measure on both. Yeah. Yeah. So I just wanted to like explain a brief application of this fact. So you might have heard these results about classical constant depth circuits asking what distributions can we sample from in constant time classically. And kind of amazingly now there's like a full characterization of this fact. Totally natural to generalize this to ask what distributions or states can we sample from or produce in constant time quantumly. It's much less clear. But this actually will answer that question for the subcase of producing pure states in constant time. Yeah, so the application, so suppose psi pure is psi equal c times 0 to the n for c a depth k quantum circuit. Okay, then suppose, oh, sorry. This is, it resolves this in the case of symmetric states. So suppose psi is epsilon close to symmetric, then psi is O of 4 to the k, epsilon close to product. Yeah. And so when epsilon is 0, you can prove this to yourself in 1 minute. If you put an n here, it's also pretty easy to argue. Removing the n is, maybe it takes a bit of work and comes for free, essentially, from this definite effect, rigidity fact. So, yeah.
So if you're a symmetric state produced by a load-up circuit, then you must be a product state?
Yeah. 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 So this is the pure case. You could imagine a situation where you apply QNC0 and then trace out some of the qubits, and only after tracing out the state is symmetric. Here, it's much less clear what is possible. Yeah, I think it's quite mysterious.
I'm sorry,
Is the circuit that needs to prepare this state have to prepare it exactly, or?
Oh, it's kind of saying, start with the circuit, call it C, let psi be whatever the circuit outputs. And if it so happens that psi is close to symmetric, then it's also essentially product.
And again, plugging in the epsilon equals 0 case, I mean, at some point when I have a depth K circuit, I am just going to be able to produce entangled symmetric states. So is there some other,
Oh, I see. Yeah.
is there some other factor that like the big O is suppressing maybe?
That's a really good question. I'd have to think about that. But yeah, you're totally right.
Also, yeah, like a similar question is like, why is that not like 2 to the k instead of?
Instead of 4 to the k?
Yeah.
Oh, it's just because like there's light cones that happen at some point, and you need to know. Yeah, like you basically you have to make this. It's typical. Like you look at backwards light cones, and you see how many qubits there are that have disjoint backwards light cones, and I think you have to pay 4 to the k instead of 2 to the k. But yeah, I mean, I could be getting the base wrong. Maybe
Oh
it's
yeah,
just 2 to the
okay,
k.
yeah, yeah, like the stand. Okay, yeah,
Yeah.
I guess.
So, yeah. Yeah. So anyway, that's that. Yeah, and maybe like one final comment is, yeah, the proof of this is like kind of like a variational argument. It seems to not, like, I wanted to prove this with information, like typical information theory kind of things, but it just like didn't work at all. So if anyone has like approaches to prove this, it'd be cool to hear.
What is the variational argument mean here?
Oh, like you you assume that you're like close to symmetric, and then you like look at derivative, you like look at Taylor expansions and make arguments and like round things to being symmetric and things like this. Yeah. So it's like calculus. Yeah.
So can you sketch how you go from this to the application?
Yeah, yeah. So what we will do is so psi is our true output. Let's say psi bar is the closest symmetric state. Okay, and then the distance from psi to prod is at most the distance from psi to psi bar plus psi bar. to prod. Okay. This, by assumption, is epsilon. And then here we have a symmetric state. Here we have product stuff. We're going to actually use data processing to consider a marginal of psi bar. So claim there exists a subset of qubits of density, little n, at least 1/4 to the k, such that, let's say, psi bar sub s is product. So this is a claim. It's totally standard in constant depth circuit stuff. Basically, you look at all your output qubits, and if two qubits are really far away from each other, then if you just marginalize on that pair, they would be product. This generalizes a bit, and you can find a big collection of them that are product when you take their marginal. So when we do data processing, we get d of, psi bar s prod. Okay, and oh wait, sorry.
Wait, but psi s is product, but why is psi bar?
Why is, say the question again?
I think psi is, which one is the QNC which was in the center? Psi is from QNC0, right?
Psi is from QNC0.
So
Right, so psi bar, oh, I might have done this in the wrong order. Yes. This is, might have done this in the wrong order. Okay, yeah, sorry. Going too fast. I'll try to make this quick because I don't want to take a bunch of time. Okay, so let's just argue this fact. The distance of psi to psi bar is at least the distance of psi s bar. This is by data processing. And this is at most the distance of psi s bar with product. And this is at most 1/4 to the d psi bar. By the lemma, right? Because neither of these had to be products, so sorry about that. Okay. Right, and so with this fact, then the distance of psi prod is at most the distance psi bar psi plus distance psi bar prod.
Wait, sorry, why is it, how do you get from the first line to the second line?
This here?
Yeah.
Because
let me spot.
this is product.
Why is that product?
Because this is the true QNC0 state, and we took the S marginal, which by the structural property is.
I guess in the first line at the top, you should remove the bar. Yeah. No.
In the first line,
Top.
Where it
More
says
higher.
sidebar.
Higher. Yeah.
oh, thank you, sorry. Sorry. Okay,
The S is coming from something, I see, okay.
yeah. And we should, yeah, okay. So now we're done, right? So this guy is epsilon. This guy is controlled by 4 to the d times epsilon.
Okay, so then.
Now we're done. Yeah, sorry for the.
So to resolve John's question, it's 4 to the k plus 1 times epsilon, which fixes your epsilon.
Oh, yes.
Okay.
Thank you.
Yeah. It's that pesky plus 1.
Yeah, yeah, yeah. Yes. Thank you.
Wait, does that resolve my question? Because when epsilon is 0, that's still 0.
Okay.
1K. Yeah, I have to get back to you on that. This,
Okay, okay, yeah.
yeah.
Okay. Maybe we should move to
Yeah.
thanks. And then the last but not least, the lightning talk is Jeff.
I see.
The x just doesn't exist after log.
I see.
So that's why. So sorry, it's not the plus 1.
The light cone.
No, I got 1.
Yeah, that makes sense.
So we're gonna hear another talk that also will tell us something about load-up circuits. So yeah, take it away.
Okay, yeah, thanks. I'm going to talk about this recent work with Daniel, who's my advisor, and Cohen. And so the title is QAC0 contains TC0 with many copies of the input. Okay, so yeah, I guess the plan is I'm going to give like a quick history of what's been studied about this QAC0 class. And then I'll jump into our results and give like a quick glimpse at one of the main techniques behind them. Okay, so first I'll define AC0 circuits, which are constant depth, polynomial size Boolean circuits. And they consist of AND and OR gates of any size. So these are just AND and OR gates that have any number of wires ingoing to them, as well as NOT gates. And so I've sort of drawn one here. And QAC0 circuits are sort of meant to be the quantum analog of these classical AC0 circuits. They're, again, going to be constant depth and polynomial size. But now they can consist of quantum AND gates and arbitrary 1 and 2 qubit gates, as well as polynomially many ancilla qubits. And so quantum AND gates, I've drawn one here. Oh, let's see. Yeah. I've drawn one here. It's sort of, you can think of it as like a generalization of a Toffoli gate. And so it just computes the AND function. Okay, so what do we know about these quantum AC0 circuits? They were first defined in this paper by Moore in 1999. And sort of the big question he poses about them is whether or not they can compute the parity function. And so this would sort of mirror what's going on with classical AC0 circuits. And it was sort of a long line of work in the 80s and 90s with a lot of really nice techniques developed showing that classical AC0 circuits can't compute this parity function. So the sort of like natural thing to ask is whether or not this quantum analog can, the sim can be proved for it. And in the I guess 27 years since, a lot of people have thought about this question and tried to prove lower bounds on QAC0 for computing this parity function, but no one has been able to do it thus far. In particular, all of these works give some lower bound on some subclass of QAC0 circuits, but they need to make a strong assumption either about the depth of the circuit, so some fixed depth bound, or the number of ancilla qubits used. And so sort of the state-of-the-art lower bounds are these two results just from the last couple of years. Depth, we know that depth 3 QAC0 circuits can't compute parity. And we know that QAC0 circuits of depth d with at most n to the 1 plus 3 to the minus d ancilla qubits cannot compute parity. But relatively few people have asked this question, which is what can QAC0 circuits do, even if we can't use them to compute parity? And so sort of the very first upper bound on what these QAC0 circuits can do was given by Rosenthal in this paper from 2020, where he shows that exponential size QAC0 circuits can compute parity, which is sort of like a trivial result classically, but requires a surprising amount of ingenuity to prove quantumly. But I'm not going to get into that for now. Yeah, but this is like essentially one of the only QAC0 upper bounds we have. And so this is part of our motivation, I guess, for the things that we study in this paper. And so, yeah, it's sort of unclear what we can even do in QAC0. I haven't really talked about this sort of fan-out issue, but fan-out is something that's permitted for free in AC0 circuits, but we don't get it for free in QAC0, and the reason is that it's equivalent to this parity function up to conjugation by Hadamard gates. And moreover, there's sort of this like insane possibility, at least before our work, which is that QAC0 could be strictly contained in AC0, at least for the Boolean function case. So this is to say that QAC0 might not even be able to compute every Boolean function in AC0, which is a pretty rare phenomenon when we put a Q on the name of a complexity class and it gets less powerful. So I'm going to talk about our results now. And the first one we have is a separation result, which is that there's a decision problem which we can do in QAC0, but can't be done in AC0P. And AC0P is just AC0, except we also get mod P gates for free for some fixed prime P. And so this is strictly more powerful than AC0, so this red sort of possibility that I had on the last page is in fact not true. And prior to this work, the types of functions that we could compute in QAC0 were like what are known as read K formulas for K is O of 1, which is like an extremely weak class of Boolean functions. So this goes beyond that. And then the second result we have, which is where the title comes from, is as follows, which is for any Boolean function f in TC0, and TC0 here is the class of functions computable by constant depth circuits that are allowed and or not gates, but also majority gates. Any function in this class can be computed in QAC0, but sort of in a strange way. So if we give a sufficiently large number of copies of the input bits, then we can compute this function in QAC0. And this is sort of an interesting phenomenon because we know that TC0 is quite a bit more powerful than AC0, but that remains true even if we give a large polynomial number of copies of the input bits. Okay, now I'm going to mention like one technique that sort of powers both of these results. But first, I'm going to talk about something that Moore proved, which is that the following tasks are equivalent, which are computing parity, preparing an n-qubit CAD state, and implementing the fan-out operation. These are all equivalent up to some QAC0 transformation. And this is the circuit that witnesses one of these equivalences. So here U is some unitary that prepares the n-qubit CAD state. And these two qubit gates are CZs. And the claim is that this circuit is going to compute the parity function. And so this is a really nice result, and it's a nice exercise to work out that this is in fact true, that the circuit computes parity. Right, so the parity function here, this is what this circuit does. What I'm going to claim is that if we replace this unitary U with instead of being able to prepare the CAD state, we replace it with a unitary that prepares the W state, which is this state here that's a uniform superposition over strings of Hamming weight 1. What this circuit is going to do is it's going to allow us to weakly compute another Boolean function. And this function is this exact n/2 function. It's sort of like majority, except it's only equal to 1 if the Hamming weight of the input is equal to n/2. So it's like exactly picking out that Hamming slice. And so I'll show here what I mean by weakly. So I'm not going to go through exactly how the analysis goes, but the claim is that when you plug x in as input and then look at the measurement on the output wire, it's going to be 0 with exactly this probability here. And what's nice about this expression is that it's exactly equal to 0 only if the input had Hamming weight n/2. And so somewhat miraculously, we get a sort of one-sided tester for this Boolean function exact n/2. So that is to say that we can compute it with perfect completeness and soundness that's like bounded away from 1 by an inverse polynomial, by 1 over n squared. And so what this means is that if we could repeat this test many times in parallel, then we could take the and of the results and boost our soundness down basically however far we want if we have the ability to do this sufficiently many times. So in particular, if we could do this like n cubed times, then we could get soundness that's like inverse exponential. The problem is we can't really create extra copies of our input bits because this is the fan-out operation, which I mentioned is equivalent to parity. But if these copies are just given to us, then we can do this boosting procedure and compute the function with super high precision. And so I've like swept a couple details under the rug, but once you can do this, you can then sort of recover any TC0 circuit you want at the cost of like additional copies, depending on like how many of these majority gates are in your circuit. Yeah, and so this circuit with the W state instead of the cat state is what we call the W test, and it's sort of the main sort of primitive that we develop. And then I guess I just have a couple of open problems to conclude with. So we've seen 2 ways in which states and Boolean functions can be equivalent sort of in this low depth model. In particular, the cat and parity example from Moore's construction, and now this like W and exact n/2 example. I guess the question is, can we find more examples? Can we develop some sort of more general understanding of when this is the case? And then the second open problem I have here is if we can achieve any sort of parallel repetition with this W test. So I just mentioned a moment ago, we need many copies of the input in order to actually boost this soundness down, but that was a bit of a lie. We can actually achieve some parallel repetition via a significantly more complicated circuit. But the question is, how much more parallel repetition can we achieve? This third question, I didn't really say anything about, but it's whether or not AC0 is contained in QAC0. So the first result I showed is that we have a separation. We have a function that's in QAC0, but not AC0. But it's still very much unclear if we can simulate AC0 within QAC0. So this would require some very different primitives, seemingly. And then finally, the big question still stands, which is, can QAC0 compute parity? And I think that's all. Yeah. So it turns out that the W state, I guess this is like somewhat related to what Joe was just talking about, but